3 coronal mass ejections are now traveling through space toward Earth, and the orbital environment they are about to slam into has just been formally measured at 67 hours from a runaway collision cascade. 67 hours. Yesterday morning, a single sunspot fired 3 major solar flares in 10 hours. The R3 radio blackout was the warning shot. What is en route behind it has not been seen on this scale since 2003, and the constellation it is about to test is twice the size it was the last time the system was stress tested. Stay until the end, because what is most likely to happen in the next 60 hours is not what the National Oceanic and Atmospheric Administration is currently saying out loud. Yesterday at 11:28 Universal Time, the X-ray detector on the GOE's 19 satellite registered a flare from a sunspot region cataloged as 4455. The flare's class was X1.07, which is the 3rd tier on the 5-level radio blackout scale that the National Oceanic and Atmospheric Administration uses to classify how badly a solar flare disrupts radio communications on Earth. The classification was R3, strong. And within seconds of the flare peak, a wide-area blackout of the high-frequency radio band rolled across the entire sunlit hemisphere of the planet. The high-frequency band is the part of the radio spectrum that aircraft use when they cross the North Atlantic and the North Pacific. It is the band amateur radio operators have used for a century. It is the band emergency response coordinators fall back to when terrestrial infrastructure fails. For about an hour yesterday, that band was unusable across half the Earth. The aviation industry has a procedure for this. Transoceanic flights fell back to satellite voice over Iridium and Inmarsat. Pilots and dispatchers continued to communicate. No flight was lost. The blackout was managed. The R3 came and went. The story is what fired off the sun at the same time as the flare. Region 4455 is on the Earth-facing side of the sun. Its location at the time of the X 1.07 peak was approximately 17 degrees north of the solar equator and 19 degrees west of the central meridian, a position the space weather community calls geo-effective because plasma launched from that part of the sun travels along trajectories that intersect Earth's orbit. Yesterday morning, in a window of about 10 hours, that single region fired 3 high-energy flares. The first was an M9.3 at 1:36 Universal Time. The second was an M7.7 at 0700 Universal Time. The third was the X 1.07 at 11:28. Each flare launched a coronal mass ejection, a giant cloud of plasma and embedded magnetic field, outward into the inner heliosphere. The first CME from the M9.3 became visible in the SOHO-LASCO coronagraph imagery at 2:13 Universal Time. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center describes the structure as a partial to full halo with a confirmed Earth-directed component. A halo CME means the cloud is traveling either toward or away from the observer. Since both SOHO and the stereo spacecraft view the geometry from different angles, the convergence of the two views on Earth-directed leaves the conclusion unambiguous. The M9.3 CME has Earth in its path. The second CME from the M7.7 became visible in coronagraph imagery at 0748 Universal Time. The morning discussion notes that the bulk of this eruption may have been deflected northward by a nearby coronal hole, a region of the sun's atmosphere where high-speed solar wind streams outward and pushed the CME off its initial trajectory. The deflection complicates the modeling. It does not eliminate the Earth-directed component. Stereo triangulation confirmed it. The third CME from the X 1.07 was still being processed in the coronagraph imagery as of yesterday's briefing window. The agency noted that if a CME is associated with the flare, it should become visible in coronagraph imagery within a few hours. Given the energy class of the flare and the configuration of the source region, the CME is expected to be Earth-directed when the imagery resolves. 2 confirmed Earth-directed CMEs from one sunspot, a third expected, all launched within 10 hours, and there is a 4th structure in the picture. On June 2nd, the day before the triple flare sequence, a slow filament eruption launched from the southwest of the sun. That cloud is not pointed directly at Earth. Its trajectory carries it past us. But the morning discussion from the Space Weather Prediction Center contains one sentence that operationally reframes everything else. The discussion notes that the June second filament's timing, source location, and relatively slow velocity mean it has a high probability of interacting with the faster CMEs behind it and changing their propagation into the near-Earth environment. That sentence describes cannibal-CME interaction. When a faster coronal mass ejection overtakes a slower one in the inner heliosphere, the two structures merge. The compound CME that emerges carries the kinetic energy of both and a magnetic field orientation that can be different from either parent cloud. The merger reorganizes the field structure. The result, when the compound cloud arrives at Earth, can be a geomagnetic storm significantly larger than either individual CME would have produced. This is not a theoretical mechanism. Compound CME interactions are the events that produce the largest geomagnetic storms in the historical record. The G5 extreme storm of May 10th and 11th, 2024, the strongest storm since 2003, was a compound event from active region 3664. The Halloween storms of 2003, which knocked out about half of the satellites in orbit at the time and forced the astronauts on the International Space Station to take cover from elevated radiation in the most shielded section of the station, were a sequence of compound CMEs. The Carrington event of 1859, the most intense geomagnetic storm in recorded history, is now widely interpreted by the heliospheric physics community as a CME that traveled through a path already cleared by an earlier CME, allowing the second cloud to reach Earth faster and harder than it otherwise would have. The configuration currently traveling through the inner heliosphere toward Earth includes the June 2nd slow filament, the M9.3 CME, the M7.7 CME, and the expected X1.07 CME. 4 discrete plasma structures launched within a window of approximately 20 hours on overlapping trajectories, with the slow front potentially being overtaken by the faster back. The conditions for cannibal-interaction are operationally present. Here is the part of the picture that is going to matter most as the next 2 to 3 days unfold. The Space Weather Prediction Center's 3-day geomagnetic activity forecast, issued at 12:30 Universal Time yesterday, the same hour the X1.07 was peaking, predicted a peaked planetary K-index of 3.67 through June 5th. The threshold for a G1 geomagnetic storm, the lowest level on the 5-level G scale, is a K-index of 5. The forecast is explicitly below G1. The rationale section reads, in plain English, no G1 or greater geomagnetic storms are expected. That forecast was issued at the same moment the same agency had already confirmed, by independent triangulation across 2 spacecraft, that 2 Earth-directed CMEs were already in transit, that a third X-class flare was peaking, and that a slow antecedent filament had a high probability of interacting with the faster clouds behind it. The eruption record and the formal storm forecast were structurally separated at the moment of the X1.07 peak. The reason for the gap is methodological, not concealment. The arrival magnetic field orientation of a coronal mass ejection, the single variable that determines whether the resulting geomagnetic storm is significant or modest, is essentially impossible to forecast until the CME crosses the L1 Lagrange point and is sampled by the ACE or DSQOVR spacecraft approximately 30 to 90 minutes before Earth arrival. The agency cannot issue a watch with unjustified confidence. The methodology produces, in moments like this one, a gap of hours to a day between the eruption record and the formal watch. That gap will likely close by the time this video publishes today. The agencies will catch up. The watches will likely be issued. But the gap existed at the moment the X1.07 fired, and the gap is the reason a viewer reading the daily forecast page yesterday would have seen, on the same screen, a confirmed R3 radio blackout in progress, and a KP forecast that said no geomagnetic storm was expected. There is a reason region 4455 was capable of producing 3 M-class or greater flares in 10 hours. The reason is in its magnetic configuration. The region is what the field calls anti-Hale. In 1919, an American astronomer named George Ellery Hale published a paper describing the magnetic polarity of sunspot pairs. He found that the orientation follows a systematic rule across the 11-year solar cycle, determined by which hemisphere a sunspot is in and which cycle phase it emerged during. About 97% of bipolar sunspot groups follow this rule. The 3% or so that violate it are called anti-Hale. Anti-Hale regions are statistically associated with disproportionate flare productivity. Peer-reviewed work, including the Ley, Ulrich, and Zhang catalog of bipolar active regions violating Hale's polarity law, has established that despite carrying on average roughly 16 times less total magnetic flux than Hale-compliant regions, anti-Hale regions produce X-class flares at a higher rate per unit of flux. The mechanism is the same complexity that makes the region anti-Hale in the first place. Subphotospheric turbulence has twisted the rising magnetic flux rope to the wrong angle, and the mixed polarity and magnetic shear that result are the conditions that drive the magnetic reconnection that powers solar flares. The Space Weather Prediction Center's morning discussion describes region 4455's specific configuration. Small negative polarity spots are developing south and west of its mature positive spot. The spots exhibit continuous flux emergence. The result is a very mixed polarity area with substantial magnetic shear. The agency identifies this as the likely source of the high-level M-class flaring from the region. Region 4,455 contains 17 distinct sunspots. Its area is approximately 330 millionths of the visible solar disk. The Macintosh classification is CKI, compact, dense, mature. The current SWPC forecast assigns the region a 75% probability of C-class flaring in the next 24 hours, a 40% probability of M-class, and a 10% probability of X-class, 10 times the typical region baseline. The most relevant recent precedent for what region 4,455 is doing is active region 3664 in May 2024. Same configuration class, same triple flare class sequence over a comparable window. The output of that sequence 13 months ago was a G5 extreme geomagnetic storm, the strongest storm since 2003. The constellation around Earth at that time was approximately 6,000 operational satellites. The constellation today is 12,000. Here is the mechanism that connects a coronal mass ejection on the Sun to a satellite in low Earth orbit. The mechanism is called Joule heating, and it is the most important thing you need to understand for the rest of this report. When a CME arrives at Earth, and when the embedded magnetic field has a southward component, the solar wind energy couples efficiently into Earth's magnetosphere through magnetic reconnection at the dayside magnetopause. The energy is channeled into electric currents that flow through the high-latitude ionosphere. The currents encounter resistance from collisions between ionospheric plasma and the neutral atoms of the thermosphere, the layer of atmosphere between 80 and 700 kilometers above the surface where low Earth orbit satellites operate. The resistance dissipates energy as heat. The heat causes the thermosphere to expand. The expanded thermosphere has higher density at every altitude. The higher density produces enhanced aerodynamic drag on every satellite passing through. That is the chain: solar wind in, magnetic reconnection, ionospheric currents, Joule heating, thermospheric expansion, drag enhancement. The chain is documented in the peer-reviewed literature. The chain is reproducible from first principles in any standard physics curriculum. And the chain has been demonstrated operationally during a specific event that the commercial satellite industry has been studying ever since. On February 3rd, 2022, SpaceX launched 49 Starlink satellites into a deployment orbit at approximately 210 kilometers altitude. A minor G1 geomagnetic storm, the lowest level on the 5-level storm scale, was in its recovery phase at the time of launch. The standard forecast had not flagged the storm as operationally significant. The launch proceeded. The thermospheric response was nonlinear. Peer-reviewed analyses published in the Journal of Space Weather and Space Climate, in Space Weather, and later in Frontiers documented the density enhancement profile. At the 210-kilometer deployment altitude, atmospheric density during the deployment window was 20 to 30% higher than pre-storm baseline. At higher altitudes, the enhancement reached 90 to 160%, approximately a doubling to tripling of atmospheric drag. The Starlink team's onboard telemetry indicated drag at the deployment altitude approximately 50% higher than during previous launches. The team issued a command sequence to put the satellites into a safe hold attitude, turning each spacecraft edge on to minimize the cross-section exposed to drag. The safe hold attitude was designed exactly for this scenario. The problem was the communications window. The satellites at 210 kilometers complete one orbit in approximately 90 minutes. Each orbit gives the ground station 10 to 15 minutes to communicate. The Starlink team was working through the queue as fast as they could. They commanded 11 of the 49 satellites successfully into safe hold. The remaining 38 did not receive the command in time, or had already lost too much orbital energy by the time the command sequence reached them. By February 7th, 2022, 4 days after the launch, all 38 satellites had re-entered Earth's atmosphere and burned up. The minor storm cost SpaceX 38 satellites in 4 days. The lesson the entire commercial satellite operations community internalized from the event is that minor storms can produce major operational consequences when the deployment conditions are marginal. The industry adjusted protocols. Deployments at higher initial altitudes. Storm window delays, faster command architectures. The constellation in 2026 is more resilient than the constellation that lost 38 satellites in 2022. But the constellation in 2026 is also 200 times larger than the launch that lost the 38. Here is where this becomes a different kind of story than a routine solar flare report. In 2018, a research team at the Outer Space Institute, a Canadian space policy organization, began work on a metric they hoped would communicate the state of the orbital environment in low Earth orbit in a single intuitive number. The framework was published as a peer-reviewed paper in Acta Astronautica in late 2025, with an archive preprint released in December. The framework name, abbreviated, is the crash clock. The crash clock answers one specific question. If every operator of every active satellite in low Earth orbit lost the ability to maneuver their spacecraft, for any reason, including a major geomagnetic storm, how long would it take, statistically, before the next predicted collision between cataloged objects would occur? In 2018, the answer was 121 days. In June 2025, the answer was 5.5 days. In January 2026, the answer was 3 8/10 days. In May 2026, the answer was 2.5 days. As of the most recent provisional update in the early summer of 2026, the answer is 67 hours, 2.8 days. The trajectory has compressed by a factor of approximately 43 in 7.5 years. On a logarithmic scale, the metric has halved roughly every 15 months. Every revision since the framework was first formalized has gone in one direction. The framework's authors have been explicit, repeatedly, that the metric does not predict a cascade. It does not measure when Kessler syndrome will start. The worst-case assumption, that maneuvering capability goes to zero simultaneously for all operators, is conservative by design. The conditions for the worst case to actually materialize are extreme and have not yet occurred in the operational era of large constellations. What the metric does measure is the slack in the system. How much margin does the orbital environment have between its present configuration and a configuration in which the failure of the maneuvering infrastructure would translate within days into a cascade-initiating collision? In 2018, the system had 121 days of slack. Today, the system has 67 hours. The reason the trajectory has gone in one direction is the population growth in low Earth orbit. The Starlink constellation alone, as of June 1st, 2026, contains 10,413 satellites in orbit, of which 10,397 are operational. That single constellation accounts for approximately 65% of all active satellites in orbit globally. The total cataloged resident space objects in low Earth orbit, including debris fragments larger than 10 centimeters, now exceeds 44,800. At specific altitudes, 775 kilometers, 840 kilometers, and 975 kilometers. The band cited most often in the peer-reviewed assessments. The density of resident objects is already above the threshold that the collision cascade modeling community treats as crossed for self-sustaining cascade. Those altitudes are the legacy of the FY-1C anti-satellite test in 2007, the Iridium-33 Cosmos collision in 2009, and the Cosmos 1408 anti-satellite test in 2021. The debris is, on human timescales, permanent. The four structures currently traveling through the inner heliosphere toward Earth will arrive over the next 36 to 60 hours from publishing time today. The question is, what kind of storm they produce when they get here. The conservative case is that the sequence arrives as a G2 to G3 storm with brief excursions toward G4, and the constellation absorbs it with degraded but recoverable performance. This is the most likely outcome by an overwhelming margin. The base rate of compound CME setups producing operational disasters in low Earth orbit is, in the documented history, low. The major operators have improved their storm preparedness significantly since February 2022. Auroral displays at mid-latitudes, some HF blackouts during storm peak, some elevated drag at operational altitudes, some elevated conjunction warning activity. Manageable. The middle case is that the cannibal-interaction between the three Earth-directed CMEs and the antecedent slow filament produces a compound storm that reaches G4 or G5 conditions. The probability of the compound scenario producing a G4 or greater outcome from a setup like this one is, in the published assessments, in the range of 15 to 30%. The May 2024 G5 storm was a compound event from a similar configuration. If the middle case materializes, the constellation gets stress tested at a level the 6,000 satellite constellation was tested at in May 2024, and finds out operationally what doubling the population means. The aggressive case is that the compound storm produces severe enough operational degradation to test the crash clock margin. The maneuvering infrastructure across operators is, for a window of hours to days, severely degraded by the combination of drag enhancement modifying all orbits simultaneously, HF communication degradation, and ionospheric scintillation degrading GPS-based orbital determination. The conjunction warning rate exceeds the operational capacity to safely handle. A near miss becomes a near collision. The probability of the aggressive case is low, single-digit percentages at the high end, possibly fractional percentages. The probability is not zero. The probability has, by the trajectory of the crash clock metric, been rising in one direction across the entire measurement window of the framework. What you should watch for over the next 2.5 days. The Space Weather Prediction Center's 3-day forecast page. The formal issuance of a G-class storm watch. If that watch is issued at G3 or above, the storm is operationally tracking the middle case. If the watch jumps to G4 or G5, the storm is tracking the aggressive case. Auroral displays at mid-latitudes are the visible from Earth signature that the storm is in progress. HF radio blackouts during storm peak, the Starlink service status page, the public statements from the major satellite operators, the Crash Clock Framework's update channel. The R3 blackout that fired off yesterday morning was the visible part of this story. The R3 came, it went, the aviation industry handled it. The story is what is en route through the inner heliosphere right now when it arrives, and what the 67-hour margin in the orbital environment around Earth looks like when a textbook compound CME setup arrives at it for the first time since the metric was published. We will be tracking this as it develops. The next 36 to 60 hours decide which case we are in.